My name is Jakub Spanhel, and I will be presenting this workshop for the 5G-ERA reference NetApp. In this workshop, we will take a closer look to some introduction to the 5G-ERA reference NetApp. We will explain the interface of our NetApp implementation, present some requirements for the robotic platforms, and try to demonstrate in some simple scenarios in the ROS2 environment and as the standalone and distributed version of the NetApp in the Kubernetes. So let me start with the introduction to the 5G-ERA reference NetApp. This NetApp aims to present concept and usage of 5G-ERA machine learning services, such as which covers tasks such as object detection with movement evaluation, object classification, semantic segmentation, and many more. These tasks may be hard to complete on smaller and low-power robotic platforms, and edge or cloud processing can be more appropriate instead for these services. And this is exactly the place for the 5G-ERA machine learning services. This workshop covers demonstration usage of such machine learning service, which provides simple face detection. And in this workshop, for now, we will omit the communication between the robots and the 5G-ERA middleware, which is service responsible for correct deployment of the 5G-ERA machine learning services or NetApps. So before we start, let's define some terms which we will be using during this workshop. We have something called machine learning service, which by which we mean that this is the machine learning service provider, such as object detection, semantic segmentation, etc. We have something called control service server, or you may see in the text even the term like machine learning control service, which is the server part of our created ROS2 service, which is responsible for generating some unique task IDs and launching new ROS nodes inside this machine learning service. And we have also the machine learning control service client, or only the control service client, which is the client part of our implemented ROS2 service from the previous definition, and this is the part which should be implemented by the robot. And for the purpose of this workshop, we also use developed robot logic service, which is again ROS2 service, which allows us on-demand starting and stopping of data processing from the robot. So, what is the concept of the 5G-ERA reference NetApp? We have two different variants of machine learning services which are provided here. One is the standalone variant, and the other is the distributed version of the NetApp or the machine learning service. For the standalone variant, it means that multiple robots can be connected to one service, and this service is only at a single location, and all the processing, processing of incoming data, the machine learning inference, and the sending back the results of the detection, or the machine learning models are done in a single application, and this can be launched even in edge or the cloud. And for the distributed version, we mean that we have some entry point for each machine learning service, which can distribute the task to multiple workers, which can be deployed almost everywhere in the internet. So for the standalone version, like I said, this represents the concept where the machine learning service logic is integrated inside a single application, and there is only ROS2 communication between the robot and the machine learning service. Data flow inside the application is based on internal queues, in our case, Python queues. It has some advantages and disadvantages. Advantages are that the processing of data inside the application is pretty fast, and latencies are close to zero because we don't need to transfer any more data over the internet, but we have only the local processing. And this kind of application are ready for image sequence dependent processing, such as object movement evaluation, where we need to get frames step by step. But it has some disadvantages as well, and this is that the possibly lower number of connected robots to a single instance of the machine learning service, which depends on hardware where the service is deployed. For the distributed version of the service, there is a combination of ROS2 communication with the distributed data and to the interface, and from the interface to the workers, we use some distributed data processing using the Celery engine, or Celery workers, and data for processing are transmitted from the machine learning service interface, which is the entry point to the workers around advanced message queuing protocol. In our case, it's RabbitMQ, but we will see it later. Again, it has some advantages and disadvantages. The advantage is that the processing of data is really distributed, and there is a possibility of scaling using multiple workers which processes the data. But the disadvantages are that the processing is much slower than in the standalone version, and there are bigger latencies because data needs to be transferred over the internet. And we have only a limited number of machine learning services which are suitable for this distributing data processing. Other important part of our 5G-ERA machine learning service is the unified communication interface, which allows us that each different service requires various types of data, and in our concept, the communication between the robot and the machine learning service is created in ROS2, and in this animation, we will see that the robot makes a request for processing data using the machine learning service. The robot sends the request through machine learning control service and begin the communication. and the machine learning service will create the topics and return its names. Then the robot will launch internal publisher and subscriber, and using these settings obtained from the response, and dedicated communication channels are created or established between the robot and the machine learning service. And after that, a robot can start sending the data, and the data are processed over the worker, and results are published back to the robot. So I will let the animation run again. So the robot will appear, he launches the control service client, and using this service, he requests to start and register with the machine learning service and waits for the communication topics. Control service server will generate unique ID and start a new node with the dedicated subscriber and publisher. This is the subscriber for the images and the publisher for the results. And these topics are returned back to the robot. Robot will launch his internal publisher and subscriber. The communication is dedicated only for this single robot, and the robot can start send the image data and process the results which are returned back from the machine learning service. So this is the basic concept which we are going to present in this workshop, and we will go step by step, which should be better for you to understand how this is implemented and why, and which steps are needed to complete from your side to use these machine learning services with your robots. So from this point, we can start with the workshop itself. Hopefully, you have your virtual machines prepared or your host systems prepared. I hope that you all who wants to take a hands-on experience, that all of you will completed the steps from the prerequisites, and that we can start with the hands-on workshop for now. From now. So first of all, we will get the newest version of the source files for this workshop. And build the ROS2 packages. So I will switch to the terminal window, and we will do actually, we will get the newest updates from the workshop repository, and build the packages. I will be using the terminal multiplexer because we will need some more terminal windows, and this is easier way to follow which window is active, and we do not have to switch between multiple terminals in multiple windows. So I download all the updates from the Git repository and